Thanks so much for the generous introduction. Oh, wow. Yeah. So I really appreciate it, and it was a pleasure to get up early. I'm an early riser anyway, and what a great set of conversations. So thank you all for making time to chat with me today. This talk that I'm going to give is going to be super informal too. So please interrupt, ask questions, tell me you disagree, and I'll kind of tell you the story of this work we did. It's a little bit weird, honestly, this topic. So as mentioned, it's this topic bootleg about this running cat. And of course, being a professor...
The recording has stopped. This meeting is being recorded.
Okay, cool. So of course, as a professor, the folks who did the real work here are this cast of characters. And they deserve all the credit for everything I'm going to talk about. It's a privilege to represent their work. So the problem we're going to look at is a really classical one. Named entity disambiguation, or mapping strings to things. So if someone asks an assistant, how tall is Lincoln? Well, one step of that process is that you have to be able to match Lincoln, the phrase, to Abraham Lincoln, the QID that's in your particular database. Just imagine we have to link it to the Wikipedia page, or Wikidata, the ID that's in it. We want to go from those strings to those concrete mappings about real-world objects, and that's what we're going to talk about. And as I mentioned, it comes up in assistance, search, information extraction. Now, you probably think about this problem, you think, well, it's got to be solved. We have lots of fancy tools, and those fancy tools are great, man. I mean, they've been really spectacular. Information retrieval and BERT work phenomenally well for a lot of these kinds of problems. And on things that are in the head that are very frequent, where you see them all the time, those tools are amazing. And very simple modifications of them get you really, really, as I'll show you, high quality, which is exciting. What I started to get interested in is what I was talking about as tail entities. These are entities that appear kind of informally, only infrequently in text, or maybe only in structured data. So for example, only 13% of entities in Wikidata have a page, and corresponding Wikipedia page, and fewer than 1% of songs in music brains have a Wikidata entry. Okay, so there are all these structured objects that a human could rightly refer to, but somehow they're not represented in these frequent textual forms that we'd like to be able to perform this disambiguation task. Okay? So that's a practical motivation. But really, like the problems that I like to work on have this kind of subtle reasoning to them. And there's subtle reasoning in the tail. So in the head, you can kind of get by with memorizing everything. But in the tail, there's kind of this you have to use some subtle clues, it seems like, to be able to actually get these disambiguations correct. And I'll talk about what those clues are by example in a little bit. But there's some headroom here. So, we often find ourselves in these problems where we're sledding very hard for 0.1 or 0.2, points of F1 on some leaderboard, and we're sweating and, so many hours are spent. And those are interesting problems because we're advancing the field. But there are also interesting problems where sometimes it's really greenfield, and sometimes those can be fun. And here in the tail reasoning, I'll show you with just, even on open data sets, but if you look at it in the right way, you can see these problems that I think are important, but also have huge potential, like these 50-point F1 buffs that I'll show you in a while. Okay, but really, it's really because these problems are fun. Okay? So the key challenges I'm going to look at here are really in two halves. One problem is that I would call it quality without engineers, and the tail has a huge amount of patterns, and it's difficult to scale and maintain. And this kind of may sound vacuous to you, so I'm going to describe to you kind of what led me here and, the very practical motivations that kind of got me into this problem. And then I'll describe a simple and largely self-supervised architecture. And really what we're after here is think about the simplest set of inductive biases we could have that would lead us to kind of good performance on the tail. That's actually what I wanted to get out. And this sets new state-of-the-arts on some named entity disambiguation benchmarks and knowledge benchmarks that people are looking at. And interestingly, there's this lift on the tail, which you could get in a variety of ways, and we got in this with this largely self-supervised architecture. So I'll describe that in the first part. In the second part, I'll talk about something else, which is related, which is what happens when you deploy these embeddings and they start to get used. And I'm pretty fascinated by this because, the world has moved to pre-training in a pretty recent shift. And so now we have embeddings that are really part of lots of products, and they're more complicated than they were before. Usually we used to embed words, but now we have contextual and knowledge and user embeddings all over the place. And I'm kind of interested in how do you maintain these things and fix them up when they're going wrong. And so we're starting at this idea of how do we debug embeddings and maintain that. And I'll give you an overview there. I should also say all of this is written up in a draft that I'm happy to give you, but we haven't publicly posted yet. All the code is posted, but the draft is still under construction as we go through it. Okay, so please, if you want, reach out and we'll send it to you. So as I said, a little project history to understand like why we looked at this stuff. And of course, like anything, it's due to a bunch of really great folks. These are Apple folks who I worked with when my company was acquired at Apple. My first PhD student, Fung. A couple of these folks were actually at the startup who was acquired. And then Charles and Benoit were kind of the executive support for this and really let us kind of run wild and ship these models to production, which is really satisfying. So the story goes like this. In late 2017, I was tasked effectively with enhancing a service that was doing named entity disambiguation, and really as a key step in a bunch of question answering, information extraction, and topic recommendation products. And I went through and I was, very happy to work on this, and I completed a high quality solution for US English, and we were kind of building a model, and I love building stuff like this. It was fun. And Fung and I, my first PhD student, we just had been acquired. We were really happy that we were, improving quality for this big industrial system, and we were going to ship it. And so it was a mostly deep model, as you would expect in 2017. It had a couple of hand-tuned knowledge graph features that we thought were, kind of the bare bones of what we were doing. But they turned out to that maintaining those features over time was becoming a challenge as like the knowledge graph would evolve. So we wanted to show this to our Apple overlords, and they're good people. I like them. They said, this is great. We love it. We're going to roll it out in English. We love to roll it out in tens of locales or languages around the world, which have different front-end products. And they said that was great, but then they also told us they were not going to give us tens of new headcount. And so what they meant is, figure out how to do this at a much larger scale. It's kind of cute that you did it for English, but we need to scale to all these different languages. And I kind of recognized then that the way I had been approaching this problem was just not going to scale, right? It was fine for academic papers that I was writing. It was fine for the problem in English, but there was no way that we could figure out how to automatically scale this without, scaling the number of engineers by the number of languages. And so that just wasn't going to happen. So we decided to start removing any form of manual bottleneck that we could find as aggressively as we could. We didn't care if quality would go down. We just cared that we could be able to ship something that was, better than what we had and in a huge number of languages. And so what was inspiring to us, research is just this inspiring place in machine learning. The Elmo paper came out and was saying, hey, we can do all this, learn all these contextual clues that we had been struggling to hand code. We can learn those nearly automatically with natural supervision. And we were doing something that was kind of similar, but not nearly as well developed as Luke and his team. And we were like, oh, that's awesome. So we were really excited by this direction. Also in that time was this thing we were building called Snorkel that was seeing, how weak supervision was getting used in various different downstream components in Google Ads. And it was basically this idea that, if you have very many different sources of data that can supervise your model, all of which are inaccurate, well, you can combine them in clever ways, and you can kind of get a statistical theory of how to combine them and kind of stitch them together in a nice way. And that's something that was in this small project. So we're like, look, these two techniques, we're going to try and basically redo this architecture. We don't care if the quality kind of goes down, but we want to make sure we remove these manual bottlenecks. That was really the motivation. Well, embarrassingly, because I had written the first version of the hand-tuned system, and we had spent a lot of time on it, this thing beat the first version of our hand-tuned model pretty handily after we built it, and that was pretty eye-opening to me. I was pretty excited about that, to be honest with you, because we've been hoping that these systems, these kind of end-to-end big systems, would really start to beat lots of clever engineering, and here they beat a not so clever engineer, which was me, but I could at least see the path that they would start to beat more clever engineers over time. So I was really excited about it. So I wrote it as this huge mess of PyTorch code, and it got integrated into a system I wrote called Overton, because it was kind of delivering on what it promised in 2018. It got put into production then, and it got good quality bumps across locales, and life was good. Like, we were really excited this thing shipped. But it was a mess. And, then I kind of wandered back to Stanford part-time at that point. And I was really left with this nagging question. Like, what actually worked? And I had trouble really in my head articulating what about this model was interesting, and why did it fix any of the things I cared about? And what was that minimal inductive bias that would have gotten us this result? Because I coded up something, and it worked, in the sense that like the numbers went up in various different ways. But I had no idea if that was the right thing to do or if something simpler would work. And so when I got back to Stanford, really, I started talking to my students, and I said, let's try and look at kind of a clean slate problem here and say, what's the simplest architecture we could build that would get us some of these properties that we had seen in production at these different places. And talking with our friends at Apple and Xiao, who had been my collaborator since grad school and in the company and now at Apple, started thinking, what could we do? So it was the simplest thing. So that's where Bootleg came in. Okay? So that's how we started to build it. We just wanted to see, could we get these kind of properties, these largely self-supervised properties in good quality, in about the simplest architecture that we can have. All right. So we were looking at named entity disambiguation. So why is this a hard problem? And actually I have tons and tons of examples, but I'll select a few to try and get you familiar with the problem. But it's a really fun problem. It's a really subtle problem. And if you haven't worked on it, it's kind of a rewarding problem, fun little kind of reasoning puzzles. So here's the goal. You have a sentence that comes in. I've underlined David and Victoria Mitchell here just for you. This is not something that's underlined in the input. This is David and Victoria Mitchell added spice to their marriage. And your goal is to identify the David Mitchell in your database. So think about that as, ID 47. And Victoria Mitchell, ID 125, whatever it is. Okay. And we want to get from that raw sentence to that map to the knowledge graph so that we can use them for a variety of downstream processing. So the first step that you do, and kind of conventionally, is you extract candidates. You run something over it which is high recall, but potentially low precision. And this isn't super hard to build in a lot of applications. Some applications it's really challenging, but most applications, if you get 32 guesses for every candidate, for every mention that's there, you can probably, with IR techniques, somewhere in that top 32, you get something like 99% of the entities that you're after. Okay. So imagine you have this first step done. Now what happens then is once you have these candidates, the reason the candidates are significant is that they're tied to information in the knowledge graph now. Now you know something about each one of those, and we call those an entity profile. So for example, for Victoria Mitchell, we know that she's a person, we know that she plays poker, that she's an author, we know some relationships, to whom she's married, where she went to school, so on. Okay. Now what we're going to do is we're going to take all that entity profile information and we're going to embed it in some way. Okay. We're going to try and embed it in a way that doesn't have to know too much about what it's embedding because we want to scale to different knowledge graphs and to different languages. Okay? So a really simple method. If someone has to rewire it for a day, that's fine. If they have to redo everything over a course of a month, then that's not going to scale. And then we're going to put this into Bootleg. And so Bootleg is the method of doing the entity payload embedding and then doing this little bit of disambiguation. And its goal here is to produce those particular entities. And it's an embedding framework with a very simple classifier, as you'll see on top. Very standard stock way of doing the classifier. The embedding is the thing that's really interesting to me. Now, one of the reasons that we're after this, when I talked about the inductive bias, and I'm trying to convince you of this, is that for things like named entity disambiguation, you want to learn information at various different levels. You want to learn kind of idiosyncratically how do you disambiguate very popular entities or certain classes of entities. So something that's specific to that entity. You want to learn how to disambiguate using relationships, as I'll show. And you also want to disambiguate potentially using types. And I'll argue that these allow us to transfer to entirely new settings. Okay, so let me give you some examples. So, for example, if you want to say, do seals sing, right? I don't know, do seals sing. But it turns out that actually one type of seal does sing. A gray seal sings. And so here, this is kind of idiosyncratic to that entity, that this is a good disambiguation for that type of seal. And so this is something that, is not a general class or property, potentially, but it's kind of, as I said, it's kind of about this entity. Now, if you look at a very related query, when did seals start singing? Well, that's actually about the singer, name seal. And so here you could kind of very loosely associate this concept singing with each. But the point is you have to associate information that's kind of phrasal with these phrases with each of the entities potentially themselves. Or potentially, you could associate it with all musicians, right? A musician has a date that they started singing, Gray seals, that's kind of an awkward question. When did gray seals start singing? I guess that could have an answer, far less common, about where they are in the historical, prehistorical record when they started singing. So the point is you can associate this phrase that you want to remember, which great things like Elmo and then successors like BERT give us, but we want to associate it at potentially different levels here. Maybe with a type, like a musician, or maybe idiosyncratically with an entity. Since at least the early 2000s, it's kind of been table stakes to be able to do collective reasoning, right? This is something I focused on a lot. Lots of people focused on a lot, and we borrowed all that work. That folks have been doing this long before I was involved in any of it. But for example, if you see the phrase David and Victoria added spice to their marriage, well, Victoria was in the Spice Girls, and probably any reasonable BERT-style approach will remember that kind of phrase is uniquely associated with her in some way. And so it will, naturally disambiguate to her, even if she's not the most popular Victoria in the data set at this time. And David, probably it would also remember him, but it would be reinforced by the fact that David Beckham and Victoria are actually married, and you knew that information. That would reinforce your belief in that these are the correct disambiguations. However, this is pretty flimsy evidence. If you change just one word, you add in Mitchell there, and you strongly get access to the fact that it's Victoria Mitchell and not, Victoria Beckham here, well, that would change all of your reasoning. And in fact, you'd have Victoria Mitchell, in this case, as a poker player and a writer, or Victoria Mitchell, the runner, or two people that are in Wikipedia with exactly that name. Now, it turns out here only one of them is married to a David Mitchell, the comedian. And so that would allow you to do this disambiguation. And so relationships themselves can have disambiguating associated phrases with them. We want to remember that. Okay. All right. So at a high level, to kind of break it down as an engineer into numbers, let's say we're looking at this snapshot of Wikipedia that has about 3 million entities. About 22% of those entities have a relationship. They participate in some relationship. 136 of those relationships occur more than 100 with 100 entities. And that's important because it means that if we learn something at the level of relationship, we can learn it kind of there once parsimoniously, potentially, and use it to disambiguate all of those 100 entities. Maybe those entities don't have any associated text, so we can't learn the idiosyncratic way that they're referred to in text, but we could use the relationship. In a similar way, find types allow us to do something that are very similar. There are about 2.8 thousand find types in like the Yago hierarchy that are used more than 100 times. Okay, and so that compression is what's allowing us to just remember, more of these things and be able to generalize. And so there's a trade-off, right? We want things that cover many, many more entities. We want this compression to happen, but if they cover many entities and they don't discriminate, like remembering something that's associated with person or people is a very general class. Maybe that helps us between people and places, but it's not going to help us between Victoria Mitchells that we saw in the last sentence. So we have to be careful about how much these types discriminate and how general they are. Okay? And we want to kind of learn those appropriate inductive biases, I would argue, at all these different levels. Now, thanks to the magic of NLP people who are super smart, we get to get a bunch of stuff for free that used to vex me. So one thing that used to drive me nuts is actually those key phrases, those contextual phrases that we saw before that are associated with entities. You used to have to figure out how to mine those from kind of IR-style technique. But now, because you can train everything kind of end-to-end and jointly, you can learn those phrases which are, not only associated with an individual, but potentially ways that people disambiguate. So if someone says Michael Jordan to you, you probably think of the statistician. But if someone says, Michael Jordan basketball player, you think of the very famous basketball player. Or Michael Jordan actor, you think of Michael B. Jordan. So there are those idiosyncratic phrases that are used actually in their disambiguation. I don't think anyone outside of this call thinks of Michael Jordan as a statistician, of course, but we should. He's the right one. Anyway, so the point is we'll talk about embedding this information at every level, but we'll borrow all that wonderful stuff from contextual embeddings to try and store effectively in a modern transformer stack, the keys, if you like, of all the different terms and phrases that they've remembered. We'll get that for free. We'll do that at the level of entities and also at the knowledge graph relations. Okay. Now, one other bit here is that richer context is often used for rarer entities. And this is another way that you can fool yourself. So if you're in the US and you say, how many people are in Lincoln? Well, that means Lincoln, Nebraska, overwhelmingly, probably you're referring to. But here, a tail entity would be Lincoln in Lincolnshire in the UK. So when you refer to that entity, you actually refer to the fact, right, that it's you use these extra disambiguating phrases. And somehow the rare entities are in fact the ones that are, that have this more interesting linguistic pattern. And so what we hope is that we can learn these kind of KG patterns nearly automatically that say, located in blank, X located in Y is a good disambiguating signal, but that may actually be fairly rare in our corpus. We may not be able to see Lincolnshire so often, but we see this pattern a bunch. And so we need to roll that pattern up as well. I'll also mention that types have affordances, and this is another thing that you would want to measure. If I say, how tall is Lincoln? Well, you're probably referring to the president. If I say, what's the cheapest Lincoln? That's the brand, the car brand. And if I say, how many people are in Lincoln? That's the place. And that's because people have heights, and brands have prices, and places have populations. In contrast, if you have, how old is blah? That actually doesn't help you at all. Could be talking about any of these, the person, the car company, or the city. So some of these patterns are very highly, discriminative and help you disambiguate, and some are not. Okay? So we have to learn those and associate those with types. So all I'm trying to tell you here is that at each level, there's an opportunity to do well here. But of course, you can start to see and hopefully imagine, if you've never thought about building one of these systems, that if you had to build each of these components manually, you would do your error analysis, and you would go plug in more manual features about the types, about the KGs, and potentially about idiosyncratic people. And you would just start to drown underneath the amount of code that you would have if someone asked you to go scale this out to 40 different locales, something like that. So we want to be able to do this, and we want the simplest way to do it. And that's where Bootleg comes in. Okay. All right, so how does Bootleg work? Well, it's going to take structured information from the tail. We already argued about why structured information is interesting. We're really interested in those entities that don't appear frequently in text, because honestly, the very popular entities, a cache is a great tool. Just memorize every way they're referred to. We're also going to talk about guidability. How do we fix these things if something goes wrong? And I'll give you one kind of toyish example, but is emblematic of real challenges we face. So how does this work? Well, here's our input and output. Remember, we had this entity payload. And what we're going to do is we're going to embed that payload. And it's going to be hopefully really simple. So idiosyncratic things, we're going to remember in the entity embedding. So every ID is going to get some indexed into this table, and we're going to associate, some 100-dimensional vector with it. That's going to be sort of the store of those idiosyncratic features. And we'll later interpret that as kind of keys into a transformer, self-attention stack. The relations, we'll do some minor pre-processing. So for every relation, we'll make sure that in the candidate list, if it's a binary relation, the other side of that binary relation is present. So the spouse has to also be present or have some information. That is, it can possibly discriminate in this downstream sentence. And then later, what we'll do is we'll also do some joint reasoning across with a very, very standard way of doing this, which looks like self-attention for information flow. Every time we see that relation, though, we'll try to embed, we'll have an embedding that's associated with that relationship, so we can learn all the ways that the disambiguating phrases that people use around spouse or alma mater, contextually or otherwise. Every find type will also be embedded, so every poker player will get access to the same vector in case there's some set of entities that are disambiguating frequently with poker players, like the World Series of Poker or something. Other phrases that may be around them, or hold them, for example. Maybe that would be remembered in a phrase like this. Same thing with author. And then the course types, like humans, buildings, people, places, things. We would remember those. And in a very natural way, we'll just project these down so that instead of having this variable length vector, we'll project it down so that it's a nice fixed size and works well with a standard PyTorch kind of stack, standard deep learning stack. Okay. All right, we'll also keep a little bit of KG metadata. I wish we kept 0 here, but we keep some because we can't learn all of those different kinds of exact equality features. And these are documented in the paper. They're intentionally minimal for us to do later downstream relationships. Yeah. So that's all we do. And then the architecture fits on one slide. You take in a sentence, you put it through your favorite BERT style model, you do that entity payload thing that I just said, you put it into 2 sets of models that are each associated with every layer of the hierarchy I just told you. There's a transformer stack for phrases and for co-occurrence. You put them together, you run all the different things through both sides, and then you put an MLP and softmax. And this is kind of amazing in one sense because, I worked on disambiguation systems, a decade ago. And this is something that a graduate student, can and did build in like a couple weeks. And this would have taken an entire PhD or, would have taken me years previously to build and get all of these signals in there. And then we just backprop through everything and pray that it gives us the right answer, which is exciting that it does, which is amazing to me still. The point of the inductive bias is we're trying to bias these models so that we pick out each of those individual phrases or each of those co-occurrence things at the appropriate level of abstraction. And so I'll talk through two tricks that kind of nudge it in the right direction that we found were really important over just running this baseline. So the first thing is training set refinement. So we're going to train in a kind of a naturally supervised way. So, there's all this web text that's around. It's linked. Very natural forever is to be able to use those links in like Wikipedia or general web text to be able to predict back various entities. So you have an original label here. You have a sentence. You have some mentions. And you have their corresponding IDs matching in sequence. Of course, there are weak labels. We know aliases of the entity, and we can include those as well. So this is looking at a particular guitarist. And we're adding his name here as a weakly supervised addition. We'll also do simple things like weak labels from pronoun and co-reference, and very simple techniques like snorkel. If these things start to conflict with each other, we'll resolve those conflicts with just a little bit of probabilistic goo. This simple refinement generates about 2x more labels and generates about 7 points of F1 on tail entities. And that's a pretty substantial amount, 7 points of F1 just by doing this. The second simple trick that we use is that we try to regularize to induce the information to be as general as possible while still discriminating. So when you hear that, you think, oh, well, I'll just regularize, throw some dropout at it. Well, if you add standard 1D dropout, which is the first thing that you would naturally try, the problem is when you zero out components of these vectors, what's going to end up happening is that the entity vectors are still so powerful, the fine level is still so powerful, that you don't end up actually being able to regularize and push information to the higher levels. It just sort of regularizes the information at the entity level. Conceptually, a better approach is to drop out the vector entirely and force you to predict without any reference to the entity, any of its idiosyncratic features, and just use the higher levels. And so we arrange this and we do this kind of 2D style dropout at each side. This is kind of a trick borrowed from our vision friends as well. This seems out to be a pretty good trick. Gives you about 8 points of F1 on these kinds of benchmarks. All right, cool. So now to some experiments, just to say like it works. So here are some. This thing may seem extremely simple.
Hey Chris, sorry, may I interrupt a little bit?
Sure, of course.
I have a question about, can you go back to the slide with the bootleg architecture?
Sure.
So I think I didn't quite follow each of the different levels of the hierarchy. So you have
so maybe
you have four phrase modules here and four entity payload modules. How exactly did you define the four different levels?
Excellent question. So if you look on the screen here, you see they're supposed to match to these four types that are here. So the entity, for example, is the piece that's going to come out of the vector that comes out of the idiosyncratically comes from every ID. The relationship is going to be the payload of that relationship for this individual entity. And so that's going to be another vector, component of the vector. The fine types, those are the poker players, those are going to be a vector. And then the coarse types are going to be a vector. And we're going to project those down into fixed dimensional pieces. And then what's going to happen here, let me just select that here, is that we're going to take the vectors and imagine that they're four separate vectors. We're going to run them through each one of the phrase modules inside the transformer, which has kind of a bunch of has inputs for the sentence and has input for the payload. So imagine that it was like as if you were training a stack that was doing, for example, just the type-based prediction. So then the type would come in, the BERT embedding for the sentence would come in, and you would try to predict whether or not David Mitchell was in this. Like, I know that Victoria Mitchell, let's say, is a poker player. Does this sentence indicate that a poker player should be here more than the rest of the sentence? And so that was fed in. So each one of those four corresponds to just each one of those four data types that we were bringing in. Relationship, coarse types, fine types, and idiosyncratic on the entity. That's what the phrase modules do.
You use the same input at the phrase module for all four types? They're all just BERT?
They're all just BERT.
Okay.
All just BERT, yeah. They're all just
Oh,
BERT.
that's interesting.
They'll stack. So yeah, as simple as possible. You should, and I think what you're getting at here is like, that doesn't make sense. You could do a much better job. And yes, there's definitely smarter ways that you could, for example, put in other information. You could train this. We tried training this with various different ways that we were masking out particular sentences that were underneath the covers. But we just wanted this is just with the absolute vanilla pieces under the covers. Wonderful question.
Cool. Thanks.
The co-occurrence looks across the entire payload, so its type is different. Think about the phrases as looking at every individual module and saying, is this individual mention present, the entity present for this mention, yes or no, that pair? The co-occurrence looks across all of them and says, do I have support for, two entities together to do this? That's just a different type.
Mm-hmm. Great, thank you.
Goes in softmax. Yeah, cool. Yeah, so back to this thing. So just an experiment. So these are recent state-of-the-art numbers. RSS, it improves by about 2 points, which is cool. Core 50, which is a pretty well-studied benchmark. It improves by a substantial amount, which is pretty nice. And then on this Ada Connell benchmark over Yago, it improves by a very minor point. This is a new Google paper. And they do something much more sophisticated in my view, I think probably smarter. But even this very vanilla baseline does pretty well. Okay, so that was the September 2020 snapshot. And if you want access to any of this stuff to improve it, like, please God, yes, we're happy to send it to you right now. Weights, documentation, code, other people are using it. We're still writing the paper as we go. But as I mentioned, I'm really interested in the tail. That's the thing that really gets me fascinated. And this is a snapshot. I apologize if these are a little bit jagged, rough experiments, so bear with me. There's no funny business going on, just intermediate snapshots. So we took Wikimedia 1 million, snapshot with 1 million, and we ran, very standard BERT style baselines over it. And if you measure the difference between the BERT style baseline and bootleg, it's about 3 points of F1. This is kind of predicting back the text that's present, doing the disambiguation. 3 points of F1 is really not that much. Why go through all this trouble of 4 extra transformer stacks? Is it really worth it? And the interesting thing is, though, on the tail, so on torso entities and tail entities, which refer to how frequently they're seen in training, you start to see that the BERT baseline starts to kind of fall off, where the bootleg falls off just a little bit less worse, a little bit less awful. Still not great, honestly. So if you look at entities that are not seen during training, the BERT baseline, is really kind of almost forced to random guess because it has to memorize those things that it's seen. Whereas the bootleg system can use the types that it's seen before or can use a relationship. And so it's able to get a slightly higher, or in this case, almost 50 points higher on F1 on these tail entity slices. And so this is something that I think in industry is still really confused, is that like people will look at these top end numbers and get really excited about how they work. But actually users are pretty sensitive to what happens in the tail, because the tail is when they're actually really paying attention, when they're giving you more information, as I mentioned before, to help you with disambiguation. And so this is when it seems like your system is dumb or smart, because I just told you X, I told you not Michael Jordan. I told you Michael Jordan the actor. Why didn't you listen to me? It's that interaction that is sometimes pretty frayed. That's not a tail entity, but you can imagine why this giving more information and getting worse results can be frustrating. And so this is one attempt to kind of fix that. So looking at this, which of those things that I mentioned actually mattered, right?
Yes, there was a question from Jason Eisner.
Oh, sure. I can't see the chat thing. Let me see. Oh, I don't see that there's a chat.
Or Jason, maybe it would be better if you ask in person.
Oh, I was just asking for more detail about in an earlier slide. Whenever you want to go back, Chris, is fine. This isn't a good time.
Oh, sure. So for the 2D dropout trick?
Yeah.
Yeah. Oh, wonderful question. So let me go back there. Yeah. So when you do the 1D dropout, just to make sure that the challenge that I'm trying to get around is clear, is these entity embeddings are kind of like a cheap trick that allow you to do dramatically better on benchmarks. So if you make the entity embeddings, just as we know, bigger and bigger, you make your embedding size bigger, you memorize more idiosyncratic terms, you do better on the benchmarks. So your incentive is to make these entity embeddings pretty large, like 256 dimensional. When you do that, you memorize all these terms. But then when you regularize with 1D dropout, even at extreme high dropout rates, you're now regularizing down to, let's say, effectively having an entity embedding with only 128 different dimensions. that's still enough information for you to for the system to want to put everything into the entity embedding where it's seeing it, where it really highly discriminates, right? So somehow, like all the gradients are going to the entity embedding and they're being updated there. Like just naturally the bias is, well, it's perfectly discriminating if I put it in this entity. If I put it in the type, it's imperfectly helping me, right? So the problem is it's kind of bouncing off the type, and the type's getting a lot of conflicting information because it's seeing a lot of different examples. When we drop out the entity embedding entirely, then what happens is you don't have the entity embedding to backprop into anymore. It's zeroed out. And so what's going to happen is the only place you can update and do better on the examples that it's seeing are indeed in the find type or the course type. And this seems to be a necessary trick for us to get it to learn this more generalizable information. Because now it's saying, if I don't know the specific entity, but because of the way our architecture is set up, I just know it's find type information, do your best with it. And that's in what sense it helps you generalize to the tail. Because in the tail, you've never seen the idiosyncratic piece that's in the entity. You've only seen the find types, which you have from the data set. Does that make sense?
Totally, yeah. In fact, I think this problem was first noticed in an ACL 2005 paper, which was looking within words, that if you have a lot of words in a gazetteer, like a lot of lists of place names, then because that does so well, because that feature of being in the gazetteer does so well, you don't even learn things like if something ends in BILLE, it's probably a place name. And so they proposed actually the same solution, which they called logarithmic opinion pools. Or you drop out the gazetteer. It's Osborne and Smith, 2005.
Okay, I'm just writing it down as we speak.
Yeah, I can send it to you.
Please do it. I'm happy. I have my iPad handy, so I'm happy to write down it. Yeah, so it seemed like a simple trick, and as I said, we had as I mentioned, we had thought of this as a trick that we were borrowing from some stuff we had done in Vision. So I think Vision people had discovered kind of similar things, but seeing it in an ACL paper would make things a lot more direct. And in the gazetteer, it's exactly the same setting. So yes, please definitely pass it on. Awesome. So just to go back here, I wanted to talk about this piece. So as I mentioned, you can look at those different pieces, the entity only, the type only pieces. How well do they do? And so you see here, the entity only does pretty well, actually. That's the kind of burst style baseline. Interestingly, and this is a little bit of an artifact of how it's evaluated. So these numbers are plus or minus with a decent plus or minus. We're still nailing them down. You see the type only does a little bit better than the entity only here. I think that's an artifact of the data set. KG only does a little bit worse, and so on. Now, the interesting thing here to me is that if you just use the types on the tail, this was getting at Jason's question, that actually provides a pretty substantial bump, and so does the KG. So that's because of this phenomenon that I was talking about earlier in our estimation, which is that we see that type associated with things in the knowledge graph, but we've never seen that entity, in the tail, or we've seen it too infrequently to learn that that's a way that people would disambiguate. Their place of birth as a disambiguation. You may think, well, okay, then maybe the types and the KGs are redundant. Those numbers are pretty close together. When you put them together, actually, they are not doing the same thing. They're used in different ways. And actually, you get a pretty nice bump from both. So there's obviously some overlap, but you get about 16 points more from using both than using either independently, which is quite nice. When we add back in the entities here, and on this test, as I said, as an artifact, we actually do worse on the tail. And this, it was from exactly the phenomenon that, has been identified, that you're going to kind of cram things into the entity, and you're not going to learn them in the most generalizable spot. And so that's why we did this regularization trick that I talked about, that kind of recovered most. Okay? So this is the kind of flow of how those things actually show up more in the tail, but don't show up in the head as much as we had seen. As you can see, the numbers on the all entity side kind of barely fluctuate based on these numbers. And on this set, they're all within noise to me, really. Maybe the KG only one is substantially lower. But the others are pretty big gaps that you're getting from doing these kind of tricks. Super cool. Awesome. All right, so I'm going to go through this quickly. Guidability. I just want to, I'll phrase the problem and show you one example and kind of not how we fix it in the interest of time. But I just want to raise it because I think it's fun to think about, and probably clever, natural language processing people have really exciting ideas about this. So, this change has happened in systems of how we build these stacks, where now you have, say Bootleg or something that's used as an embedding, and it's used in tons of downstream stuff, right? Think of how, this is the whole hugging face value proposition, right? We're going to have one embedding, and it's going to be used in all these places. Now, I was noticing in industry that folks would use our embedding, and let's say someone would use it in search, then they would use it in QA. They would notice in search that there was some bug that they didn't like. And I don't mean bug here like, oh, there's a bug in the software and it should automatically be remedied. I typically mean like there's a different way of doing the disambiguation that they would prefer, that they would like to, systematic error that they would like to fix. And so they would, naturally, being great engineers, they'd go fix their problem locally, fine tune, add something to the training set, maybe add a little widget around the side, a little bit of goo to solve the problems that they saw in the entity. And that's fine, that's a reasonable thing to do. But the interesting things to me were that they're often those same bugs, they'd appear somewhere else, and they'd be separately fixed. And so all I wanted to do is say, well, could I somehow figure out a way for people to fix these systems? And I want to fix them in a way, kind of aspirationally, that it doesn't require a lot of manual kind of jiggering of all the underlying features and everything. I want people to program these self-supervised systems by training data, right? Which is along the kind of philosophy of the way Snorkel was doing things. Could I fix these things in a way that doesn't destroy all the good properties from the self-supervised stuff that we just talked about, but somehow allows me to correct them? And so how do we debug and maintain these kind of embedding systems over time and not have to do it at these different downstream tasks? And you may look at this and say, well, 2 isn't such a big deal, just do it twice. The problem is search and QA are not 2 different people. They're probably, tens of people. And so you're then living with these kind of legacy patches kind of over time. And so it could actually become an interesting problem in the future as we start to have more of these embeddings throughout these different kinds of systems, how they interact and kind of how we fix them. So the kind of way we've been thinking about this, and these are super initial thoughts, are we want to think about how general is the error. And we like that the type hierarchy that we had before, the types and the KG and the individual text mentions, had kind of this property that they were, different levels of generality. Then we looked at several ways to change this that used all of what I would call kind of guiding the model. So could you, for example, create what we call a slice of data? And we'll talk about that in a second. Maybe if you're looking at sports data, it's dramatically different than looking at politics data. The way we disambiguate, say, in countries is dramatically different. In one case, in politics, we mean the nation state itself, and in sports, we mean its relevant sports team. We looked at augmentation. We've been fascinated with how augmentation and self-supervision interact. We've been trying to do theory about it, so we tried to do something there. And of course, weak supervision and kind of those Snorkel-style techniques. And so we're trying to figure out exactly how these work. So let me just show you one example, and then we'll kind of skip over and we can discuss more. So here's actually a fairly systematic example that you could imagine. So Japan scored an own goal against England in the FIFA World Cup. Well, it turns out that instead of matching to Japan here, we would probably want to match to their soccer team, right? And, in both Japan and England, their football teams. And so this error could be at several levels. It could be occurring only for the Japanese national soccer team, in which case we kind of want to have the fix be just specific to this entity and not disturb the others. It could be for all national soccer teams that happen to participate in something like a World Cup. Maybe the signal we think is the problem here is that the relationship between, various sporting events and the teams that participate in them is something that we should be able to broadly learn. It could happen for all sports teams and locations. As I said, maybe it's difference between talking about sports and talking about politics. And so what we did here is we looked at how to fix each of these errors at kind of different granularities, right? And so looking at things like augmentation, for example, you could take, for example, if you wanted to fix it at the entity level, well, you could take Japan and kind of fill it out in all these different places. And what we're interested in here, without going into kind of too many different details, is this question of like, which tool should you use and when, and trying to clarify it. And we're really at the early stages here. Okay? So I'm going to skip over a little bit of this. But just as I said, you can try to fix this with augmentation. You could try to fix this with weak supervision. So for example, you could say, Ronaldo used to be on Madrid, and we have, distant supervision about that. We could label some of those texts. That's sometimes easy to write a little program to do. We could do this slicing thing that I talked about that said, hey, sometimes we have a mixture of experts, where on one slice, if it's about sports, we'll predict sports teams more or less, or we'll learn those disambiguating phrases, and we'll have another expert for politics. The challenge we faced here in this kind of 2019 paper was that's too expensive for these models that are pretty massive. And so we came up with a really lightweight way that we call data slicing to do this that was in NeurIPS last year. Okay. The point that I want to make here is that these tools are super useful on the tail. And somehow this is interesting to me about how do we program this next generation of these kind of self-supervised systems. And I don't have any really strong thoughts. I just wanted to throw it out there that, like, if the world is going to become this kind of boil the ocean and pre-train, what role does the programmer play? It's like a super fascinating question to me, and we're trying to get at it. As you can see here, these different techniques are actually fairly useful, and they allow us to get higher scores on benchmarks if you care about that. But they also let us go into the tail and kind of do these surgeries to fix up systematic problems that we see in downstream models. One obligatory thing, yes, this can improve SOTA things. We'll release some results on natural queries, I hope, relatively soon. We haven't really started on it, but we'll do it soon. There's, TACRED, which is the extraction benchmark. And if you just kind of plug these things in together, indeed, Bootleg gives you, some modest boost here, I guess 0.9. I think they have a slightly higher number, but, they've just basically slammed these things in there. Okay. Awesome. So these are a couple of different examples. Okay. So that's really all I wanted to say about these things. So in conclusion, I wanted to talk a little bit about Bootleg, which is this clean, simple, hopefully open source named entity disambiguation system. It sets some new state-of-the-arts in things like RSS Core 50 and Ada, which are these different entity-specific tasks. I know people are starting to get interested again in how do we fuse knowledge in these big pattern recognition systems, which I think is a perennial question in machine learning and AI systems, and I'm really fascinated about this. I wanted to highlight this problem of learning in the tail because it was something that was like in my face every day when we were building the systems in industry and wasn't really studied as much as I could find in the academic literature. Of course, pointers that say, hey, this is where people have been studying this, or it went by a different name, you didn't find it. That's super helpful because I really want to solve this problem. On the other side of the coin, I realized that you could actually simulate this problem in several different ways. And you could simulate it with these kind of Wikipedia slices as we described. I then talked about this super nascent direction, which was admittedly rough and raw, and I appreciate you putting up with it, which is about how can we patch these models? What does it look like to have a world where everything is like these self-supervised or naturally supervised models, which are running periodically because they have to get the latest and freshest data, but we want them to somehow be fixed up and do not make the same mistake every single day when they rerun and train from scratch. And I'm just thinking about it, and maybe other people are thinking about it too, and I'd love to get your feedback. The last thing I'll mention, everything here is open source and is something you can download. We're figuring out exactly how to share these things. We have successfully shared these with other research groups who are using Bootleg, going through tutorials. It's still raw. If you'd like to have access to any of it, let me know. We will send you a draft, and if you want to send us feedback, we'd love the feedback. Especially areas or things that we've missed are always welcome. As are a lot of this area right now feels like we want to set up clever evaluations to see what is it not doing and where can we improve it. And so that kind of feedback is also really, really welcome. So with that, thanks so much for your time and attention. Happy to take any questions if there are any. Thanks.
Thanks for your talk. Questions or comments, please? We still have like 8 minutes. Kevin?
Okay, maybe I'll start. So I'm curious. So you talk about low tail stuff, which I think is super important. I'm wondering, do you have any suggestions on sort of what are good ways to run evaluations? I mean, people care about leaderboards a lot, and I mean, we could have a leaderboard just for low tail stuff, but I'm not sure if that's the right way to go about doing things. I'm wondering, do you have any thoughts on just sort of general, if we want to focus on this low tail problem, sort of what's the right way to do evaluation?
Yeah, so we've been focusing on this a lot too, and one of my students is going to release a tool with Salesforce that tries to make it easier to get into some of these slices. He's been kind of going through and collecting. Lots of folks are doing various different kind of, tail or non-head slicing. He's trying to build a tool that makes it easier to run your model against all of those slices, so that rather than having, necessarily a leaderboard, you can get like a PDF at the end of your paper inspired by other work in the ACL community that says, like, here's how well you do on various different reasoning patterns or text attacks or all that. So I think there's a software engineering almost component to it that, it's funny, he was like an RL guy, but he got super fascinated by this and decided to build it. So like, there's some stuff I think there that hopefully, if you're interested, we'll send you the tool and send you what we're thinking about. But just trying to make it easier to catalog these data slices, as we call them, over time is one direction. Because it's really about, for researchers, I think it's really more about understanding what the failure modes are and making sure that you're making progress. And so if we can share that, I think that's one piece. That's the optimistic academic part of me. The callous part of me says, I'm not sure that researchers care as much about that, all researchers. Like, if you look at natural queries, it was put out there. And it had almost no traction. There were very few papers on it, relatively speaking, compared to other more accessible leaderboards. And if you look at natural queries, it's a real thing, right? It's the queries that at one snapshot, Google wasn't getting correct. Like, it's a really serious data set in a lot of ways. But I think people shied away from it for various reasons. And so I think there's some interesting bits there about which leaderboards catch on. And I know Percy has been, thinking about this for a while, and Chris Potts has been thinking about it for a while, and Chris Manning for a while, whole group, I guess, NLP group over there. What makes these leaderboards gameable or not? And I have just been, in the pre-COVID days, I could sneak into meetings. Now it's a little harder in Zoom. I guess it's now called Zoom bombing, what my old behaviors would be, to kind of poke my head into various NLP talks and see how they think about this. But I think that's a real serious issue of how you drive progress on some of these questions in the tail. Because if you kind of leave it out there, I think you have the sense that it will evaporate. Meaning you put it out there, you put it as a leaderboard, and people will do all kinds of stuff, but you're not sure they're really making progress. And I think that's a real challenge for the field. So my best guess was this: hey, let's try and get everyone to share their slices and different forms and style of reasoning, and see if we can share them in a tool that gives you automatic diagnostics. But I mean, I don't know. Do you have better suggestions? It'd be interesting to hear your thoughts. Yeah.
No, I don't know either. But I think it seems like having a more manual approach where you're looking at the actual examples, maybe that is the way to go. It's better than just having numbers on low frequency examples.
Yeah. It is, yeah. I think you're right that my impression of kind of NLP folks, say from circa 10 years ago, which is as an outsider looking in, was I was always blown away in the talks because they had these really interesting examples, right? There was always a sense in which the examples that were in there were hard and challenging reasoning problems, and that was to me what was so attractive. And I think one of the things that I've noticed in, as an outside reader in ACL papers recently is that there are fewer of those hard and interesting examples and more of the leaderboard style numbers that are going. And in some ways that's inevitable because we have these really powerful statistical tools. But I do think it's a missing component that the, ACL community is just spectacular at. And so, if there are efforts that are going on there that you think that we should be aware of, please send a note. We're trying to engage because I think those error analysis to try and understand where these systems are failing is pretty critical. I mean, you look at like GPT-3. I mean, I don't know how this crowd feels about it, but I think it's pretty remarkable. I mean, it has a look and feel like if you could have told me that I had built that 10 years ago, I would have freaked out. I mean, it just looks awesome in so many ways. And yet it has some really catastrophic failure modes, but it's hard to figure out where they are. So that's why this kind of error and guidability is on top of my mind. I don't know what to do, honestly. I just kind of like broadcasting it. Yes.
Yeah. Thanks.
More comments or questions?
I guess there's some questions in chat. No, so the question is, you mentioned that Bootleg is a kind of simplified form of what you did for Apple. Did you mean Bootleg is a simplified form of Snorkel? Yeah, and basically asking if Snorkel's declarative labeling don't seem present in Bootleg. So Bootleg, I focused here on the embedding architecture itself. And so it was a very simplified format of that embedding architecture. I would say that I did it in Apple I'm not super proud of. Like, I don't think it was intellectually clean and rigorous. I was writing PyTorch code as fast as I could and having a blast, like trying different things. Something would work, into the stack it would go, right? Then someone would complain at my memory or my my train time was too long, I would do some other little bit of surgery. It was great fun, and like we had like a leaderboard internally, if you like, to try and see how well we were doing. But that was what I was doing. So that's what I mean by simplified. It did not have that archaeology of model. The part about declarative labeling, we adopted that in slicing and just kind of put them in kind of silently here. We didn't do anything interesting in Bootleg about how to use those. You can plug Snorkel directly in to reduce the burden. The open source Bootleg that we're going to put out doesn't have all those integrations. When we integrated it into that system I mentioned, Overton, it had all those features built into it. So you got them for free, and they do provide quite a bit of lift because you can do things like, there was a set of tools inside Apple that would let you write like things that NLP people have done for like simple regular expressions that would label tons of text for like intents, and then it would automatically get updated into the model. So that stuff was all just baked part and parcel. So the Bootleg was the simplified version of the embedding piece that was responsible for getting the tail lift on various different products. And this was the simplest way I could think to evaluate that piece. And Snorkel was just jammed on top as a way to use weaker forms of supervision and not have a problem if they all conflicted with each other, which is the other problem when you do distant supervision, right? You throw them together and they conflict, and then you spend all your time cleaning the data. Snorkel just says, don't do that if you can.
Thanks. That answered my question. It's a lot clearer now. Thank you.
Great. So we are out of time. So if there is one last question, I will allow it. But other than that, does anyone have one more question? Okay, I think that's it. So let's thanks Chris once more for a very interesting talk, and hopefully see you next time.
Thank you all so much, and please don't hesitate to follow up by email.